Now that my channel 1 oscillator has become noisy, I'm going back to use the Wenzel oscillator instead, and it's still perfectly okay. And I will not try to find what is the problem with the old channel 1 oscillator, because I can use this. The disadvantage is that the frequency is too close to 10 MHz for the direct conversion receiver to be useful, Leanrod. It's useful up till about 7 Hz from the carrier only. And then comes the problem with the zero frequency. Here I'm sending the signal from the Wenzel oscillator through my experimental unit. And now when I compare the output with the input, this is what comes out, and this is what I send in. And there is no difference. So the unit does not add anything at 1 Hz offset, which is very interesting because I had big problems with that, and it took quite some time before I realized there must be something wrong with my test oscillator that I'm feeding into this unit. Anyway, other things are interesting. If I look at 10 Hz, there is some improvement because the crystals are filtering noise away. But if I look at, let's say, 2, 3, 4, 5, 6 Hz, here it crosses the line of minus 140. But if I look at what Leanrod is saying, at 6 Hz, 5, 6, it is minus 144 almost. So, what to think about that? I think Leanrod is measuring properly. There is a good distance between the signal and the imaginary part down here. Now, since I'm using the Wenzel oscillator, the zero frequency comes very close to 10 Hz, so I cannot trust the latest values here. It says minus 151 at 10 Hz, but then there might be some contribution from the zero frequency. With Leanrod, I see something like minus 182 here at 1 kHz. I have set linear scale because then I can see more clearly. We have all the spurs down here, so I cannot read anything, but here, but the imaginary part is very close. It has its main weight here, so I should expect this to go down a little bit further if I waited long enough. On the other hand, the correlation advantage is very large. 180, well, here 182, and here 154. That's 28 decibels. So it might be a little bit too much to be reliable. But it's the same here. 1 kHz, 182 would be here, and it seems to be in good agreement. There are spurs, there are problems, but if I try to make a soft line, 182 is not unlikely. And the flat noise floor, well, there are still circles in the data points, and the imaginary part is at the same level as the signal, and that level is something like minus 197 or so. The amplitude noise is too weak to be measurable with Leanrod. It starts at 5 Hz here at minus 141, but the imaginary part is very close. And here it is only noise, probably. And higher up, well, nothing to say about that really. While I had problems with excessive noise at 1 Hertz, I tried various things, and the last thing I did, which made me understand that there must be a problem with my signal source, that was to replace the transformer on the crystal from a transformation ratio of 2.5 down to 2.0. Means 2 windings of 5 turns each. And that is what I had to produce this. Now I have put back the old transformer, transformation ratio 2.5. And there is a small difference. Not here, of course, because this is the noise from the signal I'm sending in. But at 10 Hertz, there is a small difference, maybe more clear here. Maybe 2 decibels at 7 Hertz. Not much, but I don't know where the limitations of the PN2060 is. So this is a little bit hard to say. But it is clearly better. But the time, as it happens, it's the same number of averages. And this is the old with transformation ratio 2. And here is the new with 2.5. And this looks a little bit better. There could be a change in the output impedance. I have not checked that. Leanrad shows minus 148 dBc per Hertz at an offset of 8 Hertz. So that differs still, of course, from what I see with the PN2060. Now, the specifications for the PN2060 for a 10 MHz carrier says that it should be down to minus 150 dBc per Hertz at 10 Hertz offset. So I don't know what to think, and I don't know how to verify whether this is correct or whether Leanrad is making a mistake. Something has gone wrong now. If you look at 10 Hertz, here, this is what I had recently. So there is a 3 decibel degradation, roughly. And also here. So there is a new noise source. And when I look at Leanrad, it's obvious I have a connection problem of some kind, particularly this strong event, but all the way here you can see the red, and also here. I have cleaned the BNC connectors, and that didn't help. I have connected my measurement system to a BNC to BNC female instead of going through the selective amplifier. This is to see whether there is a problem in connectors earlier in the chain, in these attenuators perhaps, or something else. Now, with only the female BNC to BNC connector, I see the same as I did when I measured the Wenzel previous time. Here is what I'm measuring now, and here is the old. And if there is a difference, here, very small, it's in the right direction. It's better now. There is a small difference here, about 1 decibel better now. And the curvature I had here before suggests that there has been some connector problems of the same kind as I have now. Poor contact somewhere. But anyway, the reason why I have problems is not in the test system, it is in the box. I have cleaned the main tuning capacitor, and this is what I see now. And here is the previous result, the one that was very good. And now I see this. Statistics is not so good yet. This is 35 averages, and this one is 256 averages. But obviously the problem was the capacitor. It's a capacitor of this kind, and I have cleaned the outer surface and also the inner surface inside here. And I use these 3 cotton pins, I don't know what they are called in English, and you can see a lot of black stuff on them. So there was a problem, and it seems it has been fixed now. For the cleaning I'm using isopropylic alcohol that I have dipped this in before doing the cleaning. Well, as it turns out, there is still a problem. Some poor contact somewhere in the box, and it affects performance, of course. This is what I see now. Not too bad, but there is a degradation as compared to this which I had when it was running without these glitches. I have replaced all tuning capacitors. There were several of them, together 220 pF. And I increased to 230 pF to make the trimmer capacitor smaller for less current in the maybe bothersome connection between the movable part and the fixed part of the trimmer. And as you can see, at least for this short time period, this is much better than that. Although it is much better now, there are still occasional glitches. But this one is different from the ones I had a lot of before. You can see that it is wideband all the way over. And I can see here it stretches from here to here. It is 5 kilohertz. So, well, another phenomenon. I don't know how often they occur. But when I look at the PN2060, the results there are very good. I can see down here and compare with the best I had before. So it is better now. And here you can see the level is at the same, but the curve is coming down a little bit. So, well, these things are rather difficult. I have made a frequency shifter to move the rubidium signal 24 Hz down. That will give a frequency for the 0 signal in Linrod, 24 Hz plus the 13 Hz that the Wenzel is above 10 MHz. So 37 Hz will allow me to see noise up to 30 Hz probably. So what I do is the rubidium source, divide by 10 to get 100 kHz, and then divide by 2048 and 4096 to get data and a clock signal to a 74 AC 74 a flip-flop. That gives me a square wave and another square wave, and they are shifted by 90 degrees with respect to each other. Then there are low-pass filters to get sine waves. And then, from the rubidium source, I phase shift by 45 degrees in opposite directions and send that into Schottky diode mixers, SBL1. And then I mix this I and Q with the RF I and Q, and then I get two signals here, and I take the sum of them by connecting the output transformers in series. That gives me the shifted signal, and I just amplify it with two amplifiers. And then I have a shifted signal to use for the PLL to my reference oscillators. The low-pass filters are third-order Sallen-K filters. 3 resistors, 3 capacitors and an op-amp, and a voltage divider at the output, 120 ohms here and 1 kilo ohm here. And these resistors are 68 kilo ohms. It's hard to see on this printout. Capacitors, 0.33 microfarads, 0.33 and 10 times smaller, 33 nanofarads. LT spice that I used to simulate and to draw that schematic diagram gives me this frequency response. A peak of about 3 decibels at 24 Hz, and then at 48 Hz, the second harmonic, the suppression is 21 decibels. Now the signals are square waves, so there shouldn't be much of the second harmonic, and at higher frequencies, suppression is of course much bigger than this. So this gives a very nice sine wave for the Schottky mixers. Now the zero frequency is at 37 Hz here, so I can do measurements well at 10 Hz. It shows minus 147 or something like that. And maybe, depending on time and noise levels, I can read up to 20 Hz or so. But there are glitches, occasional, and they degrade performance that I can see here. And I suspect the main tuning capacitor. So I will try to get rid of that. I have added fixed capacitors until the tuning capacitor has arrived in this position. It is like this. Now the contact resistance, the noisy contact resistance between the movable part and the fixed part here, no longer affects the capacitance to the hot side of the trimmer. After 7 hours and 46 minutes, this is what I see with the direct conversion receiver and lean rod. At 10 Hz here, minus 151 dBc per Hertz. At 20 Hz, a bit uncertain, but around minus 160. When I look at the PN2060 here, which has been running for the same amount of time, on the same signals, at 10 Hz I see minus 146, and at 20 Hz minus 155. So it means I have reached a result below the performance of the PN2060, which is then not quite as good as specifications say. I have to investigate this further because I cannot be 100% sure that what I read on the lean rod screen is correct. Then, of course, at 1 Hz I see the performance of the Wenzel oscillator, as always. And here at wide separations, the measurement time is not long enough. This signal has all these circles, and the imaginary part is equally strong as the real part. But the level I see here is minus 195. So, well, probably it is in that neighborhood. I will check the effect of the operating point for the source follower. Previously I found rather big differences when changing the operating point of the source follower, the biasing for the gate and how much current there is through the transistor. And now that I have removed the noise from the tuning capacitor, this should be more visible. And I have set up Linrad with a linear display of the phase noise, and I have selected the bandwidth in the baseband graph for the green trace to start here at 9.5 Hz. Means that values below that are uncertain or incorrect. But values within the green range are computed the average, which are listed here. So I see now it has been running for 10 hours that good enough information will be available below this point. Here is a spur that I will avoid, and above here the signal to noise ratio means the imaginary part is very strong. So it means it takes 10 hours to get this kind of accuracy. And I want the faster result. So I grab the right border and move it to not include the spur. Like that. Now the values here will be the average of the data points in the green range only. Means from here to here. And that average is minus 152.63. And then I will change things on the source follower to see whether that changes. Now I've changed the resistor in the voltage divider. It was 560 from 5 volts to gate and 330 to ground. Now I changed that to 220 to ground, and I will have to wait for this number here to stabilize. You can see it varies quite significantly, and obviously so, because the imaginary part, the red dots, are very close to the yellow trace, and there are even negative values. You can see there is a blue section here. So maybe 1 hour, maybe a couple of hours. After 1.5 hours, I see something unexpected. There is a degradation, about 10 decibels. And it's clear I have a problem. These noise bursts here, they were not present when I started this measurement. Something has gone wrong. Whether it is caused by my change of the resistor or whether it is something else, I don't know yet. Well, it seems I had a connector problem. I have moved the BNC connectors slightly. I mean, rotated them into their position, and it seems it helped. So I will restart the measurement of the average phase noise. And now it looks normal again. I had minus 152.63. Right now it shows minus 156. That is just at this moment. You can see these yellow lines are below the imaginary part, so they are absolutely not correct. After 1 hour and 54 minutes, the value I read is minus 151.84. And it's not quite stable yet. It goes up and down in the second decimal. What I can see at 10 Hertz here, minus 151. That is a remarkably low noise at this separation, I think. The amplitude noise is below what I can measure. The white curve is at the same level as the imaginary part. At 10 Hertz, below minus 153, probably significantly below that, so beyond reach for this system. I ran into problems. Firstly, the intermittent pulse interference that I attributed to connectors came back. So I have cleaned the connectors, and after that I had to move them a little bit, and then the problem was no longer present. I have increased the current in the transistor, keeping the same voltage on the gate with a source resistor that I change now from 330 to 180 ohms. Means that the current has increased from 16.5 milliamp to 26.6 milliamps. And I'm approaching the maximum power of the transistor, which is 300 milliwatts. And it looks promising. I see numbers here, 151 or 152 occasionally. But I have to wait quite some time because the imaginary level and the signal level are the same still. Well, 2 hours with increased power, minus 151.57 or 0.6 rather. So it's unchanged. I will go back to the original configuration and see whether I still get something a little better or whether it is the same that I see now. Well, after 2 hours, I see minus 152.1 or 0.08. It varies a little bit up and down. I will wait until tomorrow to see if that has reached 152.6 then. After 7 hours and 25 minutes, I now see minus 151.69, occasionally 0.70. So, for some reason, the very long time measurement that gave me 152.63 is not reproduced now. That's a little bit odd. It's almost 1 decibel that differs. I have removed the capacitor used for the degree of coupling. Note this thing, it was very high recently. These interferences are in channel 1. That doesn't affect the phase noise significantly. Well, what I was saying, I have removed the trimmer for coupling and replaced by fixed capacitors, polystyrene capacitors. And now I see minus 153.1, and the time is 1 hour 45 minutes. And here you see I have a problem, and you can see it's strong. It's the amplitude probably, because it is strong here but not here. So I have a probably connector problem in the channel 1 somewhere. I will look at that. But what I see at 10 Hertz now is minus 152 dBc per Hertz, and I have run the PN2060 in parallel, started it simultaneously, so it has been running on the same signals. And it comes here at 10 Hertz, it says minus 147. And I observe minus 152 with lean rod. And so I think the limitation for the PN2060 is minus 147, while the data sheet says minus 150, I think. One possible problem is the channel 1 attenuator. I have stepped it back and forth a couple of times, both the 1 dB step and the 10 dB stepping. Let's see if that helps. I left the unit running, and now 3 hours later I have an interference problem again. You see these things here. And I don't know what it is. A poor contact somewhere, presumably. There are 5 BNC connectors and 2 stepped attenuators that could cause the problem in the path from the Wenzel oscillator through my box and into the test system. And I tried to wiggle all of them a little bit, and none of them seemed to be the culprit. So I took a hammer and hit the box fairly hard, and that helped. So I have a temporary solution. I will wait and hope that the problem will come back, and I can then try to find which component is the problem. But I have done one more thing. I inserted a quarter wave cable at the input of the PN2060 to phase shift the 2 device under test inputs so they are 90 degrees phase shifted. I have delayed the signal to the DUT2 input, and it seems that has improved performance a little bit. This looks like it is going to be a little bit lower than normal. I'm not sure yet, I will wait for a while. Now, after 2 hours, the average noise within the green region from here to here is minus 152.9. And the PN2060 shows here, and the marker is at minus 148 dBc per Hertz. So it is a little bit better than it usually is, probably because of the phase shift between the 2 inputs. This here could be a problem. I don't know. If the noise that I got rid of by banging the unit with a hammer, if it originates in one of the crystals, it may not come back again. I will leave this running more to see what happens. I can look at a wider range, and it's clear I cannot see the noise above 15 Hz offset. It is too close to the imaginary part down here. After more than 25 hours, I can see that the noise problem has come back. Now at 10 Hz I see minus 146, and in the PN2060 at 10 Hz, oh, it's outside screen. At 10 Hz here it is 144.5 dBc per Hertz according to the table. That's where the marker is. And you can see it's just below 145. So it is in agreement with lean rod now that the noise level is high enough to be above the internal noise of the PN2060. And I can see it has been noisy for a long time, because this is the average over these 25 hours, and it is at a level that I know from experience is what I should have when the noise is present. I have replaced the transformer that sits on the crystal and steps up the voltage by a factor 2.5. The new transformer is not quite equal. I made it with 50% more turns and a much thinner wire. And I don't have quite the same performance as before. You can see here it says minus 150.5. And here I read 146.9. But I don't see any noise bursts here. Here is the original coil. When I made it, it was very difficult to squeeze these fairly thick wires into the holes of the ferrite, and I'm afraid I may have scratched the insulation. The ferrite is a little bit rough in its surface, and it is possible that I can have made some noisy something in here. But, of course, the problem could be something else, and it could come back then. Anyway, this is the original transformer. I made a new one using insulated wire. I have removed the other half of it, this core. This wire is tinned, and it is isolated with some unknown plastic, and the Q was very low compared to the ones having enameled wire. So I didn't even try this. The transformer I'm using now has 2 of these cores, and you can see the wire is much thinner. But there is more turns also. It is 6 plus 9. So the inductance is much higher, and the new transformer is slightly capacitive, while the old one was a bit inductive for the crystals to see. The diameter of the old wire is 0.75 millimeters, and the new one is 0.37, and that is including the enamel. So that's the total diameter that I'm squeezing into the cores. I have made a new transformer with exactly the same number of turns and the same cores as the original one. This time I'm using telephone cable. These wires are from a telephone cable, so they are copper without any tin on it, and the isolation is polyethylene, which has very low losses as dielectric. To measure Q, I have made a series resonator. With the old transformer, the primary winding had the 4 turns. I have a 4.7 ohm resistor to ground first, and then another one. One is for the input and the other is the output of the network analyzer. And to start with, I have shorted from one connector to the other with this wire. And then I can calibrate transmission. Before calibrating, it shows me a loss of about 20 decibels. And after calibration, of course, I see 0 dB. And I have removed the short circuit, and now I see the property of the series resonator that I have. So this tells me Q is 39.9, means 40, and the loss is 3.84 decibels. And I save this. And then I take the new transformer in the same configuration. Well, the new transformer has smaller capacitances between the windings because the dielectric is much thicker. But this looks good. Q is 32. It was 40 before, but the loss is only 1 decibel, and that makes the evaluation of Q inaccurate. I will have to add some more capacitance to move it to the right frequency. Now loss is only 0.5 decibels, so the Q is meaningless. I have to reduce the resistors from 4 ohms down to something smaller. I have put 1 ohms in parallel with the 4.7 ohms on both sides, and now the loss is still 0.65 decibels, and Q comes out as 88. This measurement is of course not correct. The coupling between the input and the output goes other ways also, but Q is obviously much higher in this. I put back the old transformer. And here is the old transformer. Now it says Q76 and the loss is 8 decibels. And memory, I have the new transformer. And if I look here, marker search, it was 89 and the loss is plus 7 dB. So something is wrong here. I made 2 transformers with turns ratio 7:1, means 49 times on the impedance. And then on the secondary 1 ohm resistors to ground for both transformers, because there is leak inductance and other stuff. So now I have 2 low impedances and I have connected straight across and calibrated. I had to move the resistors away from each other together with the ground point of the secondary. And now I have put a wire from the 2 low impedance points, and I find I do not have to recalibrate. Here is the old transformer in series with 47 PF. Q is 84 and the loss is 6 decibels. And here is the new transformer in series with 69 PF. And it doesn't have any loss, it has gain. I cannot explain that. What it says is nearly 3 decibels of gain and a Q above 100. So I must conclude that this is less lossy than the old transformer, and probably my low impedance points are not matched to each other. So with this transformer as a series resonator, it makes an impedance transformation that makes the signal a little bit stronger. Here is the impedance over all 10 turns of the old transformer. It says 32 microhenries, that's 2 kilo ohms inductive. I have shorted the 4 turns winding, and ideally I would like to see 0, but I see half an ohm, 532 milliohms, and 300 nanohenries, that is 19 ohms inductive. Here is what I see across all 10 turns of the new transformer. The inductance is reduced by about 50%. It is 20 now, it was 32 before. So there will be need for a bigger capacitor to compensate for that. Here is what I see on the new transformer when I have shorted the 4 turns winding. The inductance is much bigger. It was 307 nanohenry before, now it is 585. Means that the inductive impedance has increased from 19 to 36 ohms. I don't know whether that is important, but this is something I can note. It is no longer very close to 0, this impedance. But the resistive part is probably very small. It comes out negative here, which must be an artifact of the system. After 6 hours, 48 minutes. The average is not quite as good anymore. It is 152.37. And I don't know whether there has been an event here or whether it's just the improved statistics. Things may go up and down a little bit. I will make a time-lapse video to see if there are events now and then. Here is a time-lapse video. And you can see how the correlation spectra converges slowly. Now it is no longer so rapidly going down. It is minus 152.9 here, and the time is half an hour, 33 minutes, 36 minutes. And it's running, and after some time I will make a jump further down. Now it is 1 hour, and now I made a quick jump, so now it's 2 hours. And you didn't see much difference, but the imaginary part is going down and the level becomes more and more stable. Minus 152.6. Now 3.5 hours. And it's a bit interesting that the structure here seems stable. But now I take the jump to 5 hours, and there was a little difference, as you can see. And you can see here in the PN2060, it has converged at minus 147 for 10 Hertz. But here I see minus 152. And then I made a little jump. Now it is 7.5 hours. And it becomes almost a nice straight line here, or slightly curved. I have a linear frequency scale. And here was an event. And another one. I have stepped backwards in time. And then I step forward 1 frame. Have a look down here, the noise floor. It goes up by many decibels. It's 50 decibels per division, and it's the same in both channels. And then if I go 1 more frame forward, or 1 more, you can see it here, you can see the uncorrelated noise goes sky high outside the screen. And it's the average of 50 uncorrelated, so the individual one is very much stronger than the normal. And then you can see here, I go a couple of frames forward. Here, that's the contribution as a correlated part. And now this will live for a very long time, degrading the performance. And here is another time-lapse video. I have changed parameters slightly to have a better visibility. But fairly rapidly I go down to minus 152 here, while the PN2060 says minus 146.5. And it runs like this a little bit boring. I stepped forward a little, and here it is still very good. Minus 153 here. And here was a problem. And it has a little different characteristic because it lasts for a long time. I found that this, if I move this a little bit, is very sensitive. It gives this problem, and it gives problems in channel 1 mostly. But it does affect what I see in the PN2060. You see these problems. So I'm not sure exactly what that is, but it is a problem that I will try to eliminate. I have isolated the can of this capacitor, and when I measure the voltage on the can here, I see 13.4 volts, and it is slowly decreasing. And when I measure the current, I see something, and it slowly decreases. So it is in the microampere range. So there is a leakage to the can from the negative input. This capacitor is filtering the negative voltage for the system. And of course, when having different contacts, sometimes contact, sometimes not, with the aluminium in the bottom here, there are current spikes that go into the system one way or the other. The other two capacitors are isolated except at the bottom. So I put some plastic here because there could be some little pieces of aluminium, since I have been drilling on the bottom plate, that could come in here and make a sporadic contact. I have corrected an error in my setup. In front of the PN2060 I had two amplifiers, one for device under test number 1 and one for number 2. I had fed these amplifiers from the same power supply, so the noise from that power supply has been the same in both channels and degraded performance at 10 Hz offset. Now they are fed from separate power supplies, the same ones that are feeding oscillator number 1 and number 2. And now the performance at 10 Hz is minus 152 dBc per Hertz. That is a significant improvement. And Linrad has been running in parallel, and in Linrad I can read minus 151.7 or so. So they are in fairly good agreement now. Interesting, isn't it? When I display some more by changing a parameter, X gain up here, I can see a little wider in the Linrad graph. Still, minus 151.2 for the 10 Hz offset, but there is a spur at 13 Hz that happens to become negative in the as a signal, and it has a strong signal also in the imaginary part. And I don't know what that is. And it is not showing up in PN2060, maybe because of the spur removal, I don't know. And I can read the noise at 15 Hz here as minus 158. But 20 hertz, here the imaginary part comes up. So what I can read at 20 hertz is perhaps minus 161. And then there is another spur at 23 hertz. So 20 hertz, 161. 20 hertz here is here. That's also 161 in the PN2060. Now, when the system is corrected, with respect to these two amplifiers, I am measuring the Wenzel oscillator again. And there is a small difference. And I take down these values. At 1 hertz it says minus 120.8. 10 hertz minus 145.7. And when I look at lean rod, 10 hertz, it says minus 146.2. So there are small differences, but I have waited now 4 hours and 24 minutes. At 20 hertz in lean rod, I see minus 163, a little bit noisy. And here I see, well, minus 100. At 20 hertz, I see minus 153, a little bit noisy. And in the PN2060, 20 hertz is here, and that's also minus 153. To see how much noise that comes from the Wenzel through the filter, I need to know the filter response. And here I have 10 hertz sweep across the screen. So the difference between the two markers is now 0.19 decibels. And on the other side, 0.17. So 0.18 decibels at 1 hertz offset.